Okay, let us now begin. Okay, so this is week 2 of aircraft design. So I'll first discuss in brief, okay, what sir has taught in this week. So in this week, sir has discussed the necessity of estimating the weight of the aircraft, the W naught. Okay, so here W naught consists of the entire weight of the aircraft, okay, including crew, payload, uh, fuel, and the structural weight. Okay, so first we have to estimate the first the we have to estimate the empty fuel fraction. Okay, so the empty fuel fraction is the weight of the aircraft without the fuel. Okay, so the empty weight without the fuel or the payload or the crew. Okay, and then we estimate the fuel fraction. So this is the fraction of the aircraft which is filled with fuel. Okay, so these two are the important things that we have to estimate. So okay, and then we'll study the relationship of mission profile and the fuel weight. So every aircraft is designed keeping in mind some kind of a mission. Okay, so like the mission might be simply cruising, or it might be loitering over an area, or uh, it might be a fighter aircraft, so it might have to uh, fight with other aircrafts. So keeping the mission profile is kept in mind while designing an aircraft, and that changes the fuel weight or the fuel fraction. And then we'll study propeller engine and jet engine. Okay, like for propeller engine and jet engine, what is the range, endurance, okay, how to maximize these quantities. We'll study about the fuel consumption, and also what is the CL by CD that the aircraft must be flown at, okay, to maximize these quantities. Okay, so first like we'll study what is the necessity of estimating the weight. So you must understand that here we are talking about aircraft design. So like on a blank page we are designing an aircraft. Okay, so we are creating a new aircraft. So obviously when we are creating a new aircraft, we must know its size, its weight, okay, these things. So the weight is very important to estimate, okay, not really estimate, but like decide, okay. So it is important to decide the weight class of the aircraft because like if the aircraft is heavier, then its size will also increase. The wings must be bigger, okay, the engine has to be more powerful, okay, it will have larger fuel tanks, okay. So the weight is a very important thing to decide. So the total weight of the aircraft can be broken down into its components, okay. So the total weight W naught can be written as weight of the crew plus payload plus fuel plus empty weight. So the fuel, you can understand, the empty weight is the weight of just the structural components, okay, because like the empty weight is the weight without all these crew, payload, fuel, okay. And okay, so when we are designing a aircraft, the aircraft has to fly some kind of a mission, okay, or it must satisfy some kind of a requirement. Like a requirement could be that the aircraft has to fly for 1,000 nautical miles, okay, or the aircraft has to stay up in the air for 10 hours, okay. So these kinds of, so we might have requirements like R is equal to 1,000 nautical miles, or we might have endurance equal to 10 hours, okay, or we might have speed equal to 2 Mach, okay. So these kinds of requirements we have, and depending, we might also have weight requirements, okay, like this. We might have that it must carry 100 passengers, it must carry like 10 tons of cargo. So we have these kinds of requirements. So from the requirements, we can easily estimate the weight of the crew and the payload. Like if we are told that the aircraft has to carry a maximum of 100 passengers, then we can assume that one passenger weighs 70 or 80 kgs, and from there we can say that the weight of the crew is maximum of 7,000 kg. Yes, maximum of 7,000 kg. And similarly, if we are told that the weight of the payload must be 10 tons, so we know that the weight of the payload is a maximum of 10 tons. So we can generally estimate weight of crew and payload from mission requirements, but the weight of the fuel and the empty weight, it has to be found out using other means. Okay, you can guess that the weight of the fuel can also be calculated from the mission requirements, because if you if you have to fly farther away, or you have to fly faster, or you have to fly for a long duration, then you will require more fuel, right? But if you are doing a very short kind of flight, like if you're flying just for 1 hour, okay, it could be a small agricultural plane, or it could be a small aircraft that just operates on mountains, okay, it carries people from small airports to small airports. So then if your range, endurance, these are less, then you will require less fuel, but if these are higher, then you will require more fuel. Another thing is that usually we divide the quantities WF and WE. So this weight fuel can also be written as WF, and weight empty can also be written as WE. So usually we express WF and WE as a ratio of the total weight. So we just multiply and divide by W naught to get these kinds of ratios. Now, why do we do this? Is because the historical data or statistical data that is available, that is expressed in these kinds of ratios. So now moving on, the first part is estimating WE by W naught. So this is the empty weight fraction. Now you can understand that if you have to carry a larger number of crew or a heavier payload, or you have to fly for a long time, then all these things will increase. Okay, these things will increase. Okay, but to carry all these things, you need a larger structure, right? So automatically your empty weight will also increase. Like you cannot carry a large number of people in a small aircraft, and uh, so that is not possible. So if these quantities increase, then W is also increases, and vice versa. Like if we have to carry 4 5 people, then your empty weight is also lesser. So one thing is that we are not designing an aircraft from scratch. Okay, what we do is we usually select some kind of a aircraft. Okay, there are lots of aircraft models available nowadays, so we select a aircraft model which approximately satisfies the requirements, mission requirements, and then we try to improve it or improve some aspect of it. Okay, like if we have to carry 4 5 people, okay, then we select some kind of existing aircraft which carries 4 5 people, and then we try to optimize some aspect of it. Like let us say we want to optimize the range, so we'll select that base aircraft and then we'll try to optimize the range. So for this reason, the we use historical data, or not even historical data, like the current aircraft data also. The aircrafts which are flying these days currently, we can use data from them to uh, decide the empty weight fraction. So the empty weight fraction WW naught can be estimated from historical data, the weight class, and the type of the aircraft. So generally this ratio varies from zero point 0.3 to zero point 0.7, and it decreases with increase in W naught. So uh, what this means is that it is generally more efficient to build a larger aircraft. Okay, so like if I return back to this equation, so your crew, payload, and fuel. Okay, these are okay. So see, crew and payload. These are the important things that we care about. Okay, and the fuel is required to run the engine. But your empty weight, this is the weight of the structure. So in a way, this is not really helpful. Okay, so the empty, if we can minimize the empty weight, it is better, because the empty weight is a weight that we are carrying just to support all these things. Okay, it is not of use, right? Like it is not something useful that we are carrying. So uh, we would like to minimize the weight, or specifically we would like to minimize the fraction of the total weight that is empty. So what we can see is that this ratio, it decreases with increase in W naught. So it means that uh, if we if we build a larger aircraft, like if we carry a lot of people at once or a lot of cargo at once, okay, like the commercial airliners, then in that case their empty weight fraction is lesser. Okay, but if we build a smaller aircraft which can carry a small amount of people and cargo, then their empty weight fraction is higher. So we are carrying a lot of structural weight. So anyway, like we can model the WE by W naught using this kind of a equation by fitting curves to the statistical data. So this is not so this equation, okay, this is not really anything, not a not really derived from any kind of physical laws. Okay, like this is not derived from free body diagram or Newton's laws or something. This is simply like we have his so I'll show you. So we have historical data like this, that so this is your x-axis is your W naught, and your y-axis is WE by W naught. Okay, and then what we do is we take a survey of all the aircrafts in the world, and we plot these ratios. and we get these kinds of lines. Now one thing you will notice is that your x-axis is a logarithmic scale. So your x-axis is a logarithmic scale. So this means that you can see that all these lines, they are straight. So a straight line on a log plot means that there is a exponential kind of relation, okay, between this ratio and W naught. So what we do is we take a survey of all all aircraft, or all publicly available aircraft data, and we plot their ratios, and we write their, and we note their types, and we find that the aircraft generally follow these kinds of trends. Okay, now of course this is like not really limited by any physical laws, but it can be seen that they follow these kinds of trends. So what we can do is we can fit a line to these plots. Okay, like we can fit a line to these plots, and then we can write down the equation of the line. So you know that equation of line is y equal to mx plus c. Okay, but one thing is that since this is a log scale, so ultimately this ratio becomes, like this relation becomes exponential. So after doing all that conversion, we get a equation like this, where you can see that the relationship with W naught is exponential. Now in this case, your A and C are constants, and KVS is a adjustment factor. Uh, so KVS is an adjustment factor that generally varies from zero point 0.8 or zero point 0.8 to 1.05, I think. So it is almost close to 1. Okay, I think not even zero point 0.8, I think it's 0.9. So KVS is a factor which is almost close to 1, and when you want to do a detailed analysis, you can take the exact value, but for an initial guess, you can take KVS equal to 1. Okay, for an initial weight estimation. So what is KVS? So if in your aircraft you are planning on using composite materials, so the weight of the composite materials is usually lesser than the normal materials. So in that case, we use the KVS to adjust the weight fraction. So in that case, your KVS is taken as zero point 0.9 or 0.85, something like this. Okay. Also, if you use variable sweep wings, so this I have taken from the Raymer book. Okay, this point. So if you use variable sweep wings, then the KVS is increased. Okay, it is increased to 1.04 to fit the curves. Okay. So in the given statistical data, A and C are given in FPS units. So FPS is feet pound second. So here you can see some of the existing trends between the gross weight and the empty weight fraction. So this is your takeoff gross weight, which is in pounds. Okay, and this is your weight fraction. So you can see over here, these are generally small planes. Okay, sail plane, home built metal wood sail plane. Okay, home built composite flying boat. Okay, so these are all small planes. Now over, so there you can see that the weight fraction is higher. I mean the empty weight fraction is higher. So these planes they carry a lot of structural load and less cargo load. Whereas if you see over here, you have jet transport and military cargo and bomber aircraft. So they are heavier. They are very heavy, but they carry lesser empty weight. So they carry lesser structural load and more cargo and fuel. So this is empty weight fraction versus W naught. So for different types of aircrafts. So as I said, KVS is variable sweep constant, 1.04 is variable sweep, and 1 is fixed sweep. You can see that KVS is almost 1. You can assume 1 for initially deciding the weight. So now moving on, that was estimating the empty weight, but estimating the fuel fraction is even more important, and it is like both are important, but estimating the fuel fraction takes more work. Okay, so the fuel fraction of the aircraft obviously depends on how fast, how far, and how long the aircraft must fly. So if you have a car, you can guess that if you if you go very fast, then the cars will consume more fuel, and if you go for a long distance, then more fuel will be consumed. Also, let us say you don't go for a long distance, uh, you go in circles, okay, like you go in one place in circles, but you do that for a long time, then also a lot of fuel will be consumed. So the fuel fraction depends primarily on these things. uh, so the fuel fraction depends on the mission profile, and typical mission profiles consist of takeoff, climb, cruise, loiter, descent, and landing. So typically your mission profile will have takeoff, climb, then you have cruise, then you have loiter, and then you have landing. So this is the most basic kind of mission profile. There are other kinds which I will discuss. So cruise and loiter, they form the main, they consume the most amount of fuel, because you can understand, like, takeoff will take how much time? Uh, takeoff will take 5 minutes maximum. Okay, landing will also take 5 to 10 minutes. Okay, but your cruise can be for hours. Okay, your loitering can also be for hours. So these are the primary components which consume the most amount of fuel. So we'll study primarily the fuel ratio for cruising and loitering. The Okay, so the fuel weight must also include reserve fuel and trapped fuel, which account for 6% of the total fuel weight. So of course you can understand that when you're flying, you must always carry some fuel for emergencies. Okay, like let us say you're going to land in some airport, but the weather is not good, and you have to divert it somewhere. Okay, or let us say that there is some problem because of which you cannot fly at a efficient speed, then you will consume more fuel. So you need some reserve fuel to account for that situation. And there is also something called trapped fuel, which is fuel in the fuel tank which is difficult to remove, so that fuel is usually not removed. Okay, and more fuel is added on top of it. So both of these, like reserve fuel and trapped fuel, they approximately account for 6% of the total weight. I mean the total. Okay, so the reserve plus trapped fuel, they account for 6% of the total fuel. So these are some kinds of typical mission profiles. Of course, there could be lots of other kinds of mission profiles. So the first one, as I said, is the simple cruise profile. So this could be for jet transport aircraft, okay, or any other kind of transport aircraft. So in this profile, we have takeoff, then we climb to desired altitude, and then we cruise, and then there is a loitering. Okay, loitering could be like See, what happens is that an airport has one or two or three runways. Okay, so there is a, especially in busy airports, you have a limited number of runways. You might have two runways like this. Okay, and a lot of aircrafts come to these runways. uh, lot of aircrafts come to these airports. Okay, so you can consider New Delhi airport. Okay, so if you consider Delhi airport, it is the capital city, so a lot of aircraft are coming to Delhi from like within India and outside India. Okay, but Delhi airport might have, let us say, maximum of four runways. Okay, so only four aircraft can land at a time. But what about the other aircrafts? Okay, so what they do is they they come and they loiter about Delhi. Okay, so they come and they go in circles. So above Delhi or nearby Delhi, okay, they fly in circles and they wait until one of the runways is available. So when the runway is available, then they come and land. So this is the loitering phase. This is also known as a holding pattern. Okay, so after loitering, it lands. Next could be some kind of so this is a civilian mission profile, but the rest of the three, they are military mission profiles. So you could have a mission consisting of takeoff, cruising, and then combat. Okay, so you descend to some place and then you fight with some other aircraft. Okay, and you drop some kind of weapon or you drop a bomb. Okay, and then you again get up, cruise, and then you come and land. So one thing is that why are you going up to this kind of an altitude? Like why can't the mission profile be like this? Okay, you are going up, coming down, going up, coming down. So this is because it is more efficient to fly at higher altitudes. Okay, generally it is more efficient to fly at higher altitudes. So we like fly at high altitudes, but when we have to fight, then you come down to lower altitude. You could also have the fight, you could also have the combat at high altitude, but like this profile is just for an example purpose. Okay, then we have a low level strike mission. So in this case, we again take off and then we cruise, and then the requirement is low level strike means that we have to fly under the air detection radar. So when you have a radar which is looking for aircraft, okay, like this, okay, usually the radar has some kind of a lower limit. So if this is your ground, the radar systems usually they have some kind of a lower limit below which they cannot detect aircraft. So if an aircraft flies below this lower limit, it will not be picked up by the radar. Okay, so in this kind of a mission, we have to like after cruising, we have to go down to a very low altitude, which is 50 to 100 feet, 50 to 100 feet above the ground. Okay, to escape detection by radar, and then we either drop a bomb or we like hit something, and then we have to again climb back up and then cruise and then land. Then another kind of mission profile is a strategic bombing mission. In this case, the bombing is done to a faraway target. So first, the aircraft takes off, and then there is a mid-air refueling. There is a mid-air refueling. This is done to increase the range of the bomber, and then the it again comes down and bombs the target, and then it lands. So in this mission profile, the landing is done at a different airport than the takeoff. Okay, so these are some kinds of mission profiles that could be possible. Now I will discuss the now we'll specifically discuss the jet and propeller engine. Okay, what is the best range, what is the best endurance, and what CL you must fly at. Okay, one thing before this. In all of these mission profiles, you can see that the uh, cruising phase, the cruising phase is not straight, it is slightly sloped up in all of these things. So, like, can anybody tell why this is shown? So this picture is taken from Raymer's book. Okay, so what happens is that when your aircraft is flying, then fuel is burnt, right? So when fuel is burnt, the aircraft weight decreases. Okay, but the aircraft's aerodynamics do not change because the aerodynamics depend on the structure and the shape, right? So the weight decreases, but the aerodynamics remains the same. So the aircraft climbs. Okay, so if your velocity is also same, then your aircraft will climb because it is now lighter. So that is why all of these cruise sections are slightly sloped upward. So in this course, like, or at least in this module, we will assume that your cruise velocity is constant. Yes, you are right. So see, ideally, if your aircraft is losing weight and increasing in altitude, then it is going to fly in the most fuel efficient manner. But in real life, this is not possible, and like this is not permitted actually, because you have to maintain separation between other aircrafts. So like what I read is that your aircrafts, they fly in some kind of a staircase pattern. If it is a very long distance aircraft, like it is going to some other country or some other continent, then the aircraft is permitted to fly in a staircase pattern. Like for some time it will fly in this region, and then it is permitted to increase its altitude. Okay. Uh, but in this chapter, we are going to assume that your V infinity is constant. Okay. So if you want to fly at the same level, okay, but your like the weight is decreasing, then you have to uh, reduce your V infinity. Okay, so if your aircraft is getting lighter, but you want to fly at the same altitude, then you have to decrease your V infinity. Okay, so then you will fly at this. But in this chapter, we'll assume that V infinity is constant. So if your V infinity is constant, then you will gain altitude. Okay, you will climb. Okay, so Aditya has a question: why bomber not get higher altitude after refueling, although it's efficient? Yeah, I like these mission profiles are obviously very simple, okay, and they're just for illustrative purposes, okay. After refueling, it could have gone higher also. Uh, I don't know why it is drawn like this. So now I will discuss for jet and propeller engine the range and the CL basically. So your range equation is given with as this, okay. Your range is equal to V by C L by D and log of Wi minus 1 by Wi. So here V is your cruise velocity, C is your specific fuel consumption, like how much, like your rate of fuel consumption, how much fuel does your engine consume. L by D, you know, okay, L by D is lift by drag. And now what is this Wi and Wi minus 1? So what happens is that when you have this kind of a mission profile, we number each of the points. Okay, when we are calculating the weight of the aircraft, we number each of these points. Like we might say that this is stage 1, this is stage 2, this is 3, this is 4, 5. So we number all of these points, and here you can see in the formula we have Wi minus 1 by Wi. So this will be W2 by W3. Like if we want to calculate the fuel consumed in this section of the cruise, we will put this ratio W2 by W3. So if you have a simple cruise mission for civilian aircraft, then we can number all of these stages like 1, 2, 3, 4. Okay. So this is, so the range is usually done for takeoff, right? So in this case, it will be W2 by W3. You will actually also consume fuel for the climb phase. Okay, during the climb phase is not instantaneous, obviously. The climb and descent phase, they take a significant amount of time, and fuel is also consumed. So uh, these stages also it will consume fuel, but that is discussed in the book. You can refer to the book. I think i think sir has not discussed it in the lecture. So here I'll talk about this cruise phase. So like this is the range equation, so you can invert this equation to get the weight fraction. Okay, so you can invert this equation to get this. So this equation will give you W3 by W2. So the weight at the end divided by the weight at the beginning. So you can guess that you can see that when since the aircraft is flying in this 2 to 3 region, the weight will decrease. So this ratio will be less than 1, obviously. Okay. So this is given by this, so exponential of minus all these quantities, and since there is minus, so this ratio is less than 1. Now for the best range, acha, so you know the drag polar equation that we have studied in performance. For the best range, we must fly at this CL. The CL must be this, and at this CL, your CD has to be this. And if you like substitute and calculate everything, then your L by D is 0.866 or 86% of the L by D max, and your drag is 15% more than the minimum possible drag. Okay, so uh, generally, if you fly at L by D max, if you fly at L by D max, then your drag is the lowest. Drag is the lowest. Now why? Because see, if you are cruising, then you know that lift equal to weight and thrust equal to drag. Okay. Now you can change the ratio of CL by CD and cruise, but your weight will not change, na? So your lift is same. So what happens is that the drag increases or decreases. Okay, like let us say you're cruising at L by D max. So in that case, the lift is still equal to the weight, but your thrust required is lower. Why? Because your drag is lower. But now let us say that you fly at some other velocity. In that case also your lift is equal to weight only, okay, and your weight will not change, at least not suddenly, but your drag will increase or decrease, and that will change the thrust requirement. So since your drag is 15% more than the minimum drag, so your thrust requirement is also going to be 15% more. Okay, now moving on. Now we come to the best endurance. So endurance means how much time can you stay up in the air. So let me write this. Range means how far. So how far can you go? That is called the range. And endurance is how much time can the aircraft stay up in the air. Okay, so you might have some kind of a surveillance mission. Okay, uh, you might have some kind of a surveillance mission where the aircraft has to stay up in the air, okay, and it has to go over some place again and again and scan the area. Okay, you might have some kind of a, okay, this is again a surveillance mission. Okay, this was a military surveillance mission, but you could also have a civilian mission. Okay, let us say you're mapping some area. Over there also the aircraft has to loiter in this place, okay, and create a detailed map of this area. Okay, or you might have a weather aircraft which studies the weather. Now there is another concept called high altitude aircraft, which is a replacement for satellites. Okay, so you know that if this is the surface of the Earth, then satellites are very far up. Okay, and they are used for communications. Okay, they are used for communications between various points on Earth. There is a new concept which is coming up where we fly a high altitude aircraft. Let us say at 15 kilometers. We fly a high altitude aircraft for a long duration of time, and this aircraft can now also provide communication between different points on Earth. So this is called as pseudo satellite. And of course, like if you want to do this kind of thing, you will have to stay up in the air for a long amount of time. Okay, many hours. So in those cases, we try to optimize for range. We have to try to optimize for endurance. Sorry. So the endurance is given by this formula. We you know all the quantities. So again, you can invert that to get this. Okay. Now one easy thing is that uh, in this chapter, since we are assuming that the velocity is constant, you can multiply the endurance with the velocity to get the range. Like you can multiply the endurance formula with the velocity to get the range. So here you can see that I have just omitted the v. Rest of the formula is same. So to maximize the endurance, you have to fly at this CL. Now you can see that this is the CL for minimum drag. So then your CD is going to be this, and your L by D is going to be L by D max, and your drag is going to be the minimum possible drag. Okay. Now I will discuss the fuel consumption pack. Yes, yes. This one. Yes. Okay. Now we'll discuss the fuel consumption parameter C, which is there in these formulas. So for a jet engine, primarily we talk about thrust. Okay. For a propeller engine, we talk about power. But for a jet engine, we talk about thrust. So this fuel consumption is measured in the terms of thrust, and it is also written as CT. So this is like, if you write it explicitly, this is pounds of fuel consumed per pound of thrust and hours of operation. So let us say that you take a jet engine, okay, and you run it for 5 hours, okay. Take a jet engine, you run it for 5 hours, and you measure the thrust produced. You measure the thrust produced, okay, and you also measure that how much fuel it has consumed. Then if you put it into all those quantities into this formula, you will get the CT value. So let us say that it has consumed 10,000 pounds of fuel. Okay, so you will put 10,000 over here. Then you will get, then you will write the thrust T, and then you will write hours. So 5 hours of operation. So by doing all this, you will get the CT value. And your CT for a jet engine, it is measured in 1 by R unit. Okay. So what I mean is that, like, obviously you can measure it in any time format, right? You can measure it in seconds or hours or days, whatever. But the available data or available statistical data or specifications, okay, these things are available in 1 by R unit. So one thing you have to note is that in the previous formulas that I discussed over here, all the units must be consistent. Okay, the units, they have to be the same. So all the quantities such as range, velocity, fuel consumption should be in feet pound second FPS units before substituting in the formulas. Now see, they can be in any units. If you are using SI units also, it's okay, but all of the quantities, they have to be used in written in SI units. Now I will come to the propeller engine. So in your propeller engine, the range formula is given as this, and if you invert it, you get the weight fraction. So over here, your eta is your propeller efficiency factor. Propeller efficiency factor, and C is your specific fuel consumption. So I'll discuss more about C later, because in propeller engine, your C is more complicated to deal with. Now for best range, you must fly at this CL, which is the which will cause maximum lift to drag. Then your CD is given as this. Your lift to drag is equal to the maximum lift to drag, and the drag is the minimum possible drag. Now coming to the endurance, again you can see that here, since we have considered the velocity to be constant, you can divide the range by the velocity to get the endurance formula. Okay, so there is no velocity term here, so if you divide by v, you will get another new term. So this 1 by v term has come here. Then again you can invert it to get the weight fraction. So in this case, if you want to fly, if you want to maximize the endurance, then you have to fly at this CL, which gives you this CD, and your lift by drag is 86% of the maximum lift by drag, and your drag is 15% more. Acha, yes, refueling is an option for endurance. Yes, you can refuel mid-air to increase the endurance of the aircraft, but as of now, we are not discussing those things. You can like after this discussion, you can get it on the that course page. Wait a minute. So I have not uploaded it as of now, so I cannot share the link. Uh, in the course page, you have the course outline, okay, where it's written week one, week two, those things, okay. So below that, you can click on problem solving session. There you will find the PPTs and the recordings. After this discussion, I will upload it like within 15, 20 minutes. So then we come to the wait. Then we come to the fuel consumption parameter for a propeller engine. So we know that the propeller engine this deals with power and not thrust. So we talk about power in case of propeller engine. So that is why the fuel consumption parameter is somewhat like this. It is pounds of fuel consumed uh, divided by horsepower produced at the brake and hours of operation. So if this is your prop engine and this is your engine shaft, so this is known as the brake. So again, like same process, if we run the engine for 5 hours, okay, and we measure the power produced at the brake of this engine, and then we also measure the fuel consumed, then you put it into this formula to get the CBHP. So your CBHP is measured in pounds by horsepower into hour. Okay, this is the units, pounds by horsepower into hour. So another formula here is your available power is equal to thrust into velocity. So this is during equilibrium condition. Okay, during equilibrium condition, the wait, not power available. This will be power required. So power required. Okay, required power during equilibrium condition, it is equal to thrust into velocity, where like thrust is the thrust produced by the engine and velocity is your cruising velocity. So this is equal to eta into P, where eta is the propeller efficiency and P is the power at the engine brake. So the engine is going to produce some power, but some of it is lost in the propeller. Okay, so there is an efficiency factor. Uh, Now the thrust produced can be found out using this formula. Okay, how do we get this formula? We just take like this formula. Okay, so P equal to TV. Okay, so from there you can get T equal to PR by V. Okay, and then you put in your eta HP. Okay. Now the thing is that your if your units are have to be consistent, then if your units are consistent, then uh, your power has to be measured in pound feet per second. Okay, but usually power is reported in terms of horsepower. So 550 is a conversion factor between the units. So this 550 number comes by converting the units. And similarly, so then see for the case of jet engine, CT was the fuel consumption with respect to thrust. Okay, so we can derive a equivalent CT for propeller engine. Uh, we can derive a equivalent CT. So this is useful for comparison purposes. Like if you have to compare a propeller engine and a jet engine, the fuel consumption, you can use this CT value. Now, you have to remember very importantly that your CBHP, it should be in the horsepower unit. Okay, if it is not in the horsepower unit, then the 550 factor will not come. The 550 factor is just for unit conversion. You can also see that the CT factor depends on the cruise velocity. So in case of jet engine, this was independent of velocity, but in case of propeller engine, it depends on velocity. So again, like one thing you have to note that all the units, they must be consistent. All the quantities such as range, velocity, and fuel consumption should be in FPS units before substituting in the formula. So this is a summary slide of all the like propeller and jet engine. You can take a screenshot, okay, or I will post the slides, but you can also take a screenshot. Okay, now this is some specific fuel consumption trends. Okay, this is CT. You can see it's written here equivalent jet SFC, and the unit is pound per hour per pound. So this is CT, and this is Mach number, and these are for different types of engines. So this is another slide just for reference. You can also find this in Raymer's book. Now I'll discuss some simple examples. So this is the first question. Please solve. Okay, so there are some questions in the chat box. Okay, pound is not a SI unit, it is a FPS unit. But the thing is that historically the when people were initially building aircrafts, they measured things in pound, feet, and seconds. So they've noted down all the data in these units. That is why the available data is also in these units. So I think it is better that in this course or in this chapter at least, if you use FPS units, then things will be consistent. You can use SI units. Obviously, all of the formulas work for SI units also, but there is a chance that some quantity may be given in FPS units, and uh, there is some problem. Okay, then how do you know when CL by CD becomes max? Okay, so what happens is that suppose we know that CL by CD becomes max when your CL is this CD naught by K. Okay, so then what you can do, like as a pilot, okay, as a pilot, what you can do is in your calculations, okay, usually pilots they don't sit in the cockpit and they don't do math, okay. They usually have tables, okay. In either they have some of these tables memorized, or they have these tables in the aircraft itself, okay, or they might have some kind of flight computer which calculates these values. Like for these big aircrafts, commercial aircrafts, they have flight computers where you have to enter the flight profile that I am cruising at this altitude, I am going this much far, and they calculate all the quantities, okay. But for smaller aircrafts, usually the aircraft has a manual where these important things are listed. So uh, when you want to fly at L by D max, you know that the CL is this. Okay, so this CL will correspond to some kind of a angle of attack. So you know that CL equal to CL naught plus CL alpha into alpha. Okay, so from this relation, then you can get the value of alpha. Okay, so the angle of attack, and as a pilot, I can control the angle of attack by moving the elevators at the tail. So I can control the alpha. Another important thing is that when you know the value of CL, you can calculate the cruise velocity. So you know that your weight equal to half rho v square SCL. So from this you can calculate your cruise velocity. Again, like these calculations, they will be performed by some onboard computer, or they may be given in the aircraft manual. So you can calculate the cruise velocity, and if you fly the aircraft at that velocity, like as a pilot, there is a airspeed indicator. So if you fly the aircraft at that velocity and you trim it at that condition, automatically your alpha will be the required alpha value and your CL will be the CL value. Okay, so in this question, the answer is the aircraft tail. So the aircraft tail produces the aircraft stability. So what happens is that okay, so your aircraft has a wing and it has a tail. Okay, and your so like see for any kind of thing or any kind of object, it will fly stably through the air when your aerodynamic center or your center of pressure is behind the center of gravity. Okay, now I will give an example of something which is not a aircraft. Like you can consider an arrow. Okay, you can let us say that there is just a stick. Okay, so a stick has its CG at the center. Okay, and because the stick is symmetrical also, it its aerodynamic center will be somewhere over here only. Okay, it is not very away from the CG. So if you throw the stick, okay, there is a chance that it will fly in an unstable manner. Okay, the stick might rotate through the air also. Okay, but on this stick, if you put some fins at the back, then what happens is that they uh, the fins they shift the aerodynamic center back. Your CG remains the same approximately, but the fins they shift the aerodynamic center back, and then the stick, like which has now become an arrow kind of thing. So the arrow then flies stably through the air. It doesn't flip around or rotate. Now, why this is the case? The case is because let us say you have an object, any object, and this is your CG, and your aerodynamic center is somewhere in front. Okay, and this object it deviates a little bit from the flight path. So this is your velocity. It deviates a little from the flight path. What happens is that this deviation it causes more lift. Okay, so this more lift causes it, it causes it to turn more. So in the next instance of time it becomes like this. So it deviates more and then it becomes unstable. Whereas if your aerodynamic center is at the back, if your aerodynamic center is at the back and suppose there is a deviation, then this lift it causes it to return back to its original state. So therefore, like for any general object, if your aerodynamic center is at the back of the CG, then it flies in a stable fashion. So so for aircraft also this condition must be satisfied. Your aerodynamic center has to be back of the CG. Now what happens is that since your wings they carry most of the load of the aircraft, your wings are located approximately close to the CG. Okay, so if your CG is here, the wings aerodynamic center will be somewhere over here. Okay, it is usually a bit forward of the CG. Okay, but it is very close. Okay, and this configuration it is either unstable or it may be neutrally stable. Okay, like it may be just stable or it may be just unstable. Okay, it is not really sufficient. But when you put a tail at the back, the tail acts like these fins. Okay, so this shifts the total aerodynamic center very far back, and it makes the aircraft stable. Because see, now what happens is that when there is a deviation from the flight path, the tail produces a restoring force, which that since now it is at the back, it produces a restoring force which uh, brings it down to the flight path. And the further away the tail is, the more stable it's going to be. But of course, like you do not want very high stability, because then it is impossible to intentionally move it. This is the next question. So your weight is 1000 kg. Okay, let me calculate. So this is the closest one. This is the next question. So in this case, yes, the answer is C. So when an aircraft is in a static equilibrium, it means that the the summation of forces is zero and the summation of moments is zero. Okay, but it says no other things. Okay, nothing else is mentioned. Okay, your aircraft controls may or may not be zero. Because what happens is that, like, let us say that you are flying at a low velocity. Okay, you're flying at a low velocity. So to maintain lift at that low velocity, you need a higher angle of attack. So let us say that you're flying at a low velocity. So your V is low. So when your V is low, uh, to sustain the weight, your alpha must be high. Alpha must be high. Okay. So now how will you create this situation? You will have to deflect the elevator. So the elevator is here. You will have to deflect it upwards to create this nose up situation. Now this when you are doing this, when you are the aircraft is still in static equilibrium. Okay, because the forces and the moments are zero, but your elevator deflection is not zero. The elevator has to be deflected to maintain this nose up attitude. Now the elevator deflection may be carried out by the pilot, or it may be in a trim condition. Okay, so from the your aircraft stability and dynamics, you might remember that there is a concept of stick fixed and stick free stability. So your pilot may actually hold the aircraft stick in place to maintain the elevator deflection, or he may turn the trim tab, which will do the same thing. This is the next question. So sea level atmospheric conditions, so your rho is 1.225 kg per meter cube. Okay, so now moving on to the next question. It- So your alpha stall is 15 degree and your CL alpha is 0.09 per degree. Acha, and your this is a symmetric airfoil, so CL naught is 0. So what you can simply do is you can find the CL max. So CL max is in this case, चलो, CL max is going to be CL naught plus CL alpha into alpha stall. So this is, in this case, this is going to be 0.09 into 15, 1.35. So then your V stall, acha, over here in W by S you have to multiply by G, okay, because this is in kg per meter square, but you have to write it in Newton, Newton per meter square. So I get 22.055 meter per second. So this one. Acha, now this is the next set of questions. So please try to solve this. So aircraft has a wing area of 23.69. And this is your CD naught, this is K, this is aspect ratio. Calculate L by D max. So you know that L by D max occurs when CL equal to root over CD naught by K. So we can calculate this, okay. This is 0.559, okay. And then we can calculate the CD. You know that CD is equal to 2 into CD naught at this case, like in this case. So this is 0.046. So then L by D max is going to be CL by CD at this max condition. So this is 12.15. So okay, so this one. Then incident calculate CL at min drag. We have already done this. So this is this one. Okay. Calculate velocity at minimum drag. So this will be again the same formula. Acha, don't forget to convert from kg to Newton. what is the value of the minimum drag in Newton? So remember that this also means that what is the value of the thrust in Newton, because in cruise condition thrust equal to drag, so your engine must produce this much thrust. So again we can calculate it from, sorry, half rho v square SCD. So this is 3659 Newton. So another thing that you can do is you can calculate the uh, thrust by weight, which is 3659 by 45. Okay, so you can see that the thrust by weight ratio is 0.0822. So this means that to lift such a large weight, like this is approximately 4.5 tons. Okay, so to lift this weight, you need a thrust that is just 8% of this weight, or for approximately you can say 10%. So to lift 4 tons, you require 400 kg of thrust. So this is what makes these aircrafts efficient, because you require very low thrust to lift large amounts of weight. This is the next question. So in this question, of course, you know that point A, which is this point, it corresponds to minimum power required. Like you can even see from the graph, you can see from the graph that the power requirement changes with the velocity. Okay, and this point is at the minimum, so obviously this is the minimum power required point. And in another way also, we know that, we know from calculus that the minimum occurs when the slope is equal to 0. So in this case the slope is equal to 0, so that is why this is a minimum power point. And point B is the uh, point of CL by CD max. Okay, so this point, this is the point of CL by CD max. So this we have learned it in the uh, performance course. Okay, so so see what, how is this point defined? Okay, so what you do is, this is your PR by velocity curve. Okay, this one, this is your PR by velocity curve, and then you draw a line from the origin. Okay, and wherever this line creates a tangent, wherever this line creates a tangent, that line, that point is the point of CL by CD max. I can give a short proof. I can give a short proof. So you know that the power is equal to thrust by thrust into velocity. So okay, as I said that CL by CD max. Okay, when does this happen? This happens when the drag is minimum. Okay, because uh, okay, not this, not CD, but your drag is minimum. So this happens when your drag is minimum because your lift has to be the same. Since the lift has to lift the weight, okay, and the weight is same for both the cases. Lift is same, only the drag can change. So CL by CD is maximum when drag is minimum. And in cruise, drag is equal to thrust. So this also implies that your thrust is minimum. So what I can do is I can write power as thrust into velocity, and then I can write thrust as power by velocity. Okay, now I can differentiate thrust with respect to velocity. So I will get dp by v minus, no wait, I'll get 1 by v dp by dv minus 1 by v squared. Okay, and at minimum thrust this is equal to 0. So you can write, wait, p by v square. Okay, dp by dv minus p by v square equal to 0. Okay. So then you can write that okay, you can cancel one v from here, and you can write p by v equal to dp by dv. Okay. So this is the relation that we get at minimum thrust. Now the what is this slope? The slope of the curve at any point is dp by dv. Okay, and p by v means that any line originating at the origin. Okay, any line in this graph which passes through the origin, it will have some kind of relation like this, p by v equal to some constant, right? So when both of these quantities match, that is when we get minimum thrust. So we have a line originating at the passing through the origin. Okay, so a line passing through the origin, so it satisfies this condition p by v, and it is also equal to the slope of this graph over here. So at this point both these conditions are satisfied, so this is a point of minimum thrust. Okay, so this is the next question. So here suppose you have some kind of a mission Okay, we'll write the mission segment like as we have written 1 and 2. So over here at point 1, the weight is 2700 kg, and at point 2, the weight fraction is 0.85. So it means that here the weight is 0.85 of W. So how much fuel it has consumed? So of course, like here we'll assume that the change in weight is because of the burning of the fuel. Okay, and there is no other factors. So of course, then the fuel consumed will be the weight at point 1 minus the weight at point 2, which is W minus, okay, so W1 minus 0.85 W1, which is 0.15 W1. So here you can substitute the value of 2700 kg. This gives 405 kg. Okay, so moving on. So an airliner with a takeoff gross weight of 5100 kg is cruising with a fuel weight fraction of 0.280. Then what will be the weight of the fuel? Okay, so this is again pretty easy. So the gross takeoff weight is 5100 kg and fuel fraction is 0.28. So then of course the fuel weight will be 0.28 into W naught. Okay, now I am going to discuss a problem which sir has discussed in class. Okay, so I'll discuss the same problem. If anybody has questions, they can ask me. So in this question, there is a aircraft. There is an aircraft which has to cruise. It has to perform a cruise mission, and you are given this information. So the range is 1500 nautical mile, which is equal to 9,114,000 feet. Okay, and the cruise velocity is given as 0.6 Mach, and so this corresponds to 0.6 into 994.8 feet per second. Okay, which is 596.88 feet per second. Uh, so when we so this is a high bypass jet engine. So high bypass jet engine. So in that case, the CT is given as 0.5 per hour, and you have to convert it into per second. So I am trying to bring all the units in FPS units. Okay, so this is the data that is specified in the requirements. Okay, so this is what is was specified in the requirement. For this, I am using historical data. So this turns out to be, you have to divide by 3600 and we get 1.389 into 10 to the power minus 4 per second. And when you are cruising with a jet engine, we cruise at L by D max. Okay, no, wait. No, we don't cruise at L by D max, we cruise at 86% of L by D max. So here you can see that a high bypass jet engine, it has, for cruise, it has C value of 0.5, okay, um, which is in hour. So the units are 1 by hour. And we know that for jet engine, when we want to maximize the range, wait, when we want to maximize the range, we fly at 0.866 L by D max. Okay, so here I am writing the L by D max is 16. So now we have to find out the fuel fraction. Okay, so L by D max is 16. So we can say that L by D is 0.866 into 16. So this is 13.86. Okay, then we can use the range equation. So the range equation was this, V by C L by D Wi minus 1 by Wi. So this is W1 by W2. Okay, and now we can invert this equation. Uh, so we can invert this equation to get W2 by W1. Okay, so now all the units are consistent. Okay, they are all in FPS units. So you can substitute it into the formula to get the answer. So your range is 9114000 into CT, which is 1.389 into 10 to the power minus 4. Your velocity is 596.88 and L by D is 13.86. Mm-hmm. Yes. Yes, wait. So this is I'm saying, like after this I'll write. Okay, so W2 by W1 is 0.858. Okay, but this is not equal to the fuel fraction. Uh, why? Because this is the ratio of the aircraft weights at these 2 points. Okay, so the fuel fraction will be the weight that is reduced. Okay, so if you so the fuel fraction will be W2 minus W1. This is the fuel consumed by W1. Okay, and no, sorry, the fuel fraction will be W1 minus W2 by W1 because weight at point 1 is higher. Okay, so now if you divide by W1, you get 1 by W2 you get 1 minus W2 by W1, so which is 0.14. So your fuel fraction, uh, your fuel fraction for this segment of the flight is 0.14. Okay, of course there are other things like if you are taking reserve fuel and trapped fuel into account, then you have to multiply this weight by 6% more. But for basic assumptions, this is correct. Okay, now for the book. um, the book is Aircraft Design: A Conceptual Approach by Daniel P. Raymer. I don't know that. I'm also writing this in the chat. Okay, so that is it for today. Uh, like I am concluding today's discussion, so we'll meet again next week. Okay.